Okay, so yeah, good afternoon. I'm Erol Evangelista from the Mayan Lab, and yeah, today I'm going to be discussing or have a lecture about knowledge graph, and how to like build knowledge graph for biomedical research data. And here's just an outline of the lecture. First, we're going to start a bit with databases, and then graph databases, and then work on learning about Neo4j, which is one of the more popular graph database. And we'll learn how to serialize and load data in Neo4j. And then Neo4j has this way of querying the data sets. So we'll learn about Cipher query language, and if we have time, we'll also discuss a little bit. This is a little bit different, which is how to like build a graph web-based or a web-based UI on top of our knowledge graph. So let's start with databases. So maybe you've probably heard of databases, and when you think about databases, you probably think about tables. And this table, for example, I have a grocery, and we have an inventory. So so I can have a table of the items in my grocery, the price of that, expiration, how much I have of those items, and then which supplier is supplying me. And from this, already have I can already like get several information. I can like query what items need to be refilled, what items are expiring soon, and where I could buy those items. And you can potentially expand this a bit. We can have several tables or several date tables in our where we can put different other datas. For example, we can have a table of suppliers wherein we have the name of the supplier, their contact information, maybe their website. And then another useful, perhaps if I have a grocery, is that I can have the supplier and an item that the supplier supplies, and then the cost of that item when you buy it from that supplier. So for example, in this one, you can easily query which supplier supplies the cheapest oranges, and you can see here that Cabbage Incorporated has like the cheapest oranges. So I may want to buy that from that supplier, yeah, if I want to get like the cheapest oranges. And this is basically the whole idea of databases, wherein we put our data, we put our information in this table, wherein we can easily go back on that, query it, and then extract useful information in it. And that's actually um, the basis of relational databases. So relational databases, the idea of this are they are just all tables. So you can have multiple tables, and then you can query those tables. You can define relationship, you can link those tables. But yeah, at the very basic, they are all tables. So one thing that's good about this relational databases is that we have different ones. So we have, these are some of the most popular one: Postgres, MySQL, SQLite, which is this is just really lightweight. But the good thing about this is that even though this we have like different relational database system, is that there is just one query language that so if I know how to query Postgres, it's typically really just the same thing, same grammar, same key terms when I use it to MySQL or SQLite. So it's really it's easy to, the way they did this is that it's really easy to move from different platforms, because each of this has their own pros and cons. So it's actually really easy to move from one platform to another. And yeah, so that's what makes it um really easy to develop using this relational databases system, which is the traditional database system that we know. So as an example, so we have this relational database table. So I have an example of here wherein we are tracking collaborators. So we have information here. Um, between like author 1 and author 2. We say that Ryu and Lana collaborated with this paper, and then this is the journal. And then we also have information with author of the institution that author 1 and author 2 belongs with. The problem with this is that you can see already here that there are some sort of a redundancy with like the data, right? So you know, I mean, we know that he's associated with JBU, but it's actually repeated here. So the relation, there are several redundant information, and so you know, and that can pose an issue. So this is what they call in computer science as like the unnormalized database, wherein there's redundancy issue. And the problem here is that if this becomes big, if you have like a, you know, the list of all of authors in the world or something like that, if this table becomes really big, it can get you know, the size of this will become really enormous, and you just have like lots and tons of data redundancy issue. And to fix this, um we have this normalization step, wherein this is an extra step that we do to configure our database so that it improves our data integrity and reduce those redundancies. So for example, here we define 3 tables, which is actually just the same that as what we had previously, or like same information from what we have previously. So we have here 3 tables: authors, collaboration, papers, wherein we just list the authors. So we have the information for the name and the institution, and we have this ID. For the papers, we have like the paper and then the journal, and then we have this ID. And the collaborations table, this will be probably the biggest table, but you know, instead of having like all of those redundant information with view JBU here, and then paper 1 or paper 2 NAR, paper 2 NAR here, simplified it, and we just put all of this as IDs. And you know, where in each ID is just linked to this to another ID from another table. And this is actually where the relational information, relational term from the relational database is. So you know, the tables have relationships wherein it's linked by this IDs. And you can see here, if you want to find which authors have collaborated with both Jesse and Lei. So what we can do here is that we can join these tables based on their proper respective IDs. So we can see here, so Jesse and Lei, the ID is 3 and 4. So, and these are mapped here, 3 and 4, 3, 4, 3 and 4 here. So see it here. So this is for Lei, and this is for Jesse. Now we can now look at which author they have collaborated with, which is this one. They both collaborated with, which is number 2, so 3 and 4, and number 5, so 3 and 4 here. And so so 2 points to Lana and 5 points to Jim. So we can say that Lana and Jim both collaborated with Lei and Jesse. Now, the problem with this is that, okay, we have normalized table, it's good, it's less redundant, but the thing is, you have to work with joins. So you're basically joining the tables based on the IDs. And the problem here is that it can get expensive. So imagine if collaborations table is like really big, or maybe it's not just 2 tables that you're combining. If you're combining multiple tables, multiple relationships, you're trying to figure it out, it can get really expensive. And yeah, if the tables are bigger, then that means that you're spending so much time. So when you say expensive, that means you're either spending so much the computation or finding the answers takes so much time or so much memory. So it can that's what I meant with expensive. So and this can be less ideal, especially, you know, if we have bigger tables and you have like multiple relationships or multiple connections that we want to join. Now, enter graph databases. So this is the main focus. So for graph databases, we see that it's actually stored in the database as graph. So all of these connections are stored directly as a graph instead of tables. So you can see here that we have the nodes, which are the authors, and then each node has information. So the name is view, and then the institution is JBU or something like that. And then there is a link. So each link means that these two authors have collaborated. And for example, this View and Lana, they've collaborated with this paper, which is paper 2, and then the journal is NAR. So the question of who collaborated with both Jesse and Lei is just a matter of finding which neighbors, so or the neighbor which is connected node, they have in common. So for here, we see that Jesse and Lei both share Lana and Jim as their neighbors. So, and this, we already have like several algorithms that does this path finding, neighbor finding stuff really quickly. So graph databases are able to utilize those quick graph traversal algorithms so that they're actually really optimized for these types of query. And we can see that so I mentioned joins can really be expensive, and you can see here if we are trying to find, or if we're trying to join over several nodes maybe, so you can see this kind of query can really get expensive when you are using those joins on relational databases. But for graph databases, we already have like algorithms that work best for this. And this one is a many-to-many relationship, wherein we're just finding neighbors of multiple nodes. And this is also really fast for graph databases. And also hierarchies can also be tough for other types of databases, but it's really simple when you're using graph databases. So those are just some of the benefits of the graph databases. And if we're used, so there's a pros and cons in here. And what I can say is that if your data is, you have connected data, wherein there are links with the connections between like two different entities, then graph databases can have its benefits, especially if if your data is more of like a networked one. And so yeah, so here are just some pros and cons. So first, since we had like different pathfinding algorithms on graph databases, it's really easy to find hidden connections between objects. As I mentioned, deep hierarchies is easy to explore because it's just a simple algorithm. Patterns and paths between two nodes are easy to find. It's just like, again, graph traversal, and it handles better complex many-to-many relationship. Now, for the cons, first, I mentioned earlier with like relational databases is that there is a uniform query language, wherein if you're working with Postgres, if you're working with MySQL, you can work easily between them, with like minimal changes maybe. But it's the query language, which is SQL, is standard query language, is what they use. But for this one, there are like different graph databases, and each of them have their own sometimes proprietary language that they're using. So it might be harder to move from one database to another, to like one database system to another. Of course, there are works on producing like a standardized language, but currently there's no standard language that's being used across all of these platforms. Another thing is that, as I mentioned, there are like pros and cons, is that if it's not really optimized for basic queries such as aggregation, what I mean here is, for example, if you want to find the sum of like a whole of some stuff. So for relational database, you're just summing one column of the row of a table, which is really easy, and really fast. Or maybe you're trying to find the mean, the median, or something like that. If you're doing aggregate stuff, it's relational databases are really optimized for those. And yeah, so here are some examples of graph databases. So Amazon has this Neptune, we have Infinite Graph, and then the most popular one currently, or rather one of the most popular one is Neo4j, which is what we will be discussing next. So just a checkpoint if you have any questions. And also here are some online resources regarding graph databases. So here are some introduction of what graph database are, and then here are just some comparison between graph and relational databases.